Well, good morning, good afternoon, and good evening, and welcome back. Uh, okay, so without further ado, let's start. So as I promised on Friday, I'm going to go over solutions to the homework problems. Just a second. Sorry, just there is something funny here. Okay, yes, fine. Sorry about it. I'm going to go over the solutions to the homework problems. Now, I have to say, in the case you submitted solutions, I haven't had time to look at the solutions at all, so it is entirely possible that some of the solutions are perhaps more elegant than what I'm going to say. So please feel free, if you think something can be done in a better way, please feel free to go ahead and tell me. Okay, so I'm going to go over all the questions one by one, and I'll basically give some hints. And if you think that more hints would be a good idea, or more detailed hints, then definitely I'll be happy to say a little bit more. Yeah, sorry. Yeah, okay. All right, so here is the first problem. Find the separable C-star subalgebra A of the norm ultra power of the car algebra and an automorphism of A that does not extend to an automorphism of the car algebra. All right, so here I think, yes, so U stands for non-principal ultrafilter on the natural numbers. And just no point of this exercise is to see that all this business about types, elementary equivalence, elementary submodels, and so on is necessary because as you may remember, when we were constructing many automorphisms, so an ultra power like this, we started not just from automorphism of separable subalgebra, but from an automorphism of a separable elementary submodel of the car algebra. And what we proved is that automorphisms of separable elementary submodels can always be extended to bigger and bigger and bigger separable elementary submodels, and using continuum hypothesis eventually to an automorphism of the entire algebra. Now here, so what is the trick? Well, there are several ways to approach this. I'll first say the easy way, and then I'll say a few more things about the right way to do it. So first thing to notice is that 4x4 matrices form a unital subalgebra of M2 to infinity. And of course, M2 to infinity is a unital subalgebra of its ultra power by just diagonal embedding. So here, I'll just write 1 here. So to emphasize, this means that we are talking about unital embedding. Now, why does that matter? Well, what really matters is that if you look at the diagonal, sorry, I just pressed the wrong button when my phone reminded me that class is about to start, so I got into snooze, and it's apparently impossible to interrupt snooze, to cancel snooze. If you know how to do it, let me know, please. So here, the diagonal matrices form a unital subalgebra of M4. And what are diagonal matrices? Well, just a copy of C to the fourth. Okay, one more thing. Now, okay, so what is C to the fourth? So it's all diagonal matrices. Let me call this A. So what is A is set of all things of the form X, Y, Z, T, 0, 0, where X, Y, Z, T are complex numbers. Now, I look at subalgebra B of A, which looks as follows. So B is x, 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 okay, z. Just diagonal matrices which have the property that the first three entries are equal and the fourth one is different. So again, x and z are complex numbers. So of course, B is isomorphic to complex numbers squared. And what is automorphism of B? Well, there is only one non-trivial automorphism. So phi automorphism of B, just phi sends x, 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 z to z, 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 x. So you're just swapping the two copies of the complex numbers. This is an automorphism. Now I claim that phi doesn't extend to ultra power or to the Car algebra. Now, what is the reason for that? Well, basically, the reason is, I mean, I'll just say one word, trace, or okay, tracial state. What is the point? Or basically, I just exhibit statement about these elements the elements of the algebra B that is not preserved by phi. So note, so there exists V such that okay, V I should be saying where V in M2 to infinity, such that actually, you know what? I should introduce some notation. So let P be this matrix 1, 1, 1, 0. Right, so that B is a C-star algebra generated by P and the unit. Now, there exists V in M2 to infinity such that V star V is less or equal than P, and VV star is equal to 1 minus P. I mean, just take V to be the following. So it is, here I have 0, 1, 0, I think. Did I get? I hope I got it right. So, and everything else is 0. I'll draw the whole matrix. Right, but on the other hand, there is no V in M2 to infinity such that VV star is less or equal than P, and V star, right, and sorry, I'm making this a bit messier. If I interchange P and P star, such that V star V is less or equal than 1 minus P, and VV star is equal to P. Why is that so? Well, because of trace. Because there is no such partial isometry in any of these matrix algebras, right? And so because M2 to infinity has a unique tracial state. Now, why is that so? Well, okay, let me just say that, which is because each n2 to n of C has a unique tracial state. Right, so you have inductive limit of C-star algebras. Each one of them has unique tracial state. Definitely, this is a linear algebra for any matrix algebra. And now, if you have tracial state of the entire algebra, you restrict it to those subalgebras. Each time you get that unique tracial state, it is norm continuous, so it has to be that. And unique tracial state tau, and tau of P is 3/4, right? So P is a diagonal matrix. So it's we're talking about normalized trace. It's 3/4, and tau of 1 minus P is 1/4. And one more thing, tau of VV star has to be equal to tau of V star V, right? Because that's what being tracial is about. And therefore, this here cannot happen. And that's it, right? So we have an isomorphism. Now, I wanted to do this from the scratch. Basically, a completely acceptable solution was just to say that, oh yes, I should say one more thing. This, let me just emphasize this here. So this, what I circled in green, this can be expressed in a formula. So by Walsh's theorem, it still holds in the ultra power. Right. So here I am cheating a little bit here. I mean, basically, when I say cheating, I mean there are a few more details to work out. You cannot say exists in a formula. You can just say that infimum over something is equal so and so. It is not clear that the infimum is attained. It is in this case, but you don't even need to worry about that. Even if it's not attained, you see these numbers here, 1/4 and 3/4 are far enough from one another. So you don't even need to be attained, even by V, which is approximately doing this, you can get a contradiction. Okay, so this was a sketch of what is going on there. Now, right, so what I wanted to say is a perfectly acceptable answer would be, there is a fact, which is actually not trivial, it needs to be proved, that this algebra here also has a unique trace. It is not true in general that if you have a C-star algebra with unique tracial state, then its ultra power has unique tracial state. It's actually false. There is a very nice result of Lionel Robert, which provides a counterexample to that. The C-star algebra, which has unique tracial state, but ultra power has many tracial states. But in this particular case, everything is nice. Okay, so basically, any automorphism is going to preserve the tracial state. Now, the fact is that if you look at a billion unital subalgebra of the algebra which has unique tracial state, then what that unital subalgebra looks like, if it's a billion, it is continuous functions on some compact space, compact Hausdorff space X, And now, what does tracial state look like? So if you have tau, which is tracial state, well, actually, well, any state, but if you look at any state, if you restrict it to C of X, what it corresponds to, well, really there is a measure mu, which is a probability measure on the space X. And so what is tau of some F? It is simply integral F d mu. Right, so every state on C of X is of this form. So this is basically Riesz representation theorem. Okay, so now we have a compact Hausdorff space. So in my case, that compact Hausdorff space was just 2 points, and the measure was just the atomic measure. One atom had a measure of 3/4, one had measure of 1/4, and I swapped the atoms, and that doesn't extend. But you could do almost anything. You know, you can take X to be unit interval and make sure that this tracial state is Lebesgue measure, and then just find some auto-homeomorphism unit interval which doesn't preserve measure, and that would not extend. So basically, this was the idea. Okay, so the second exercise, prove there exists a separable C-star algebra B such that every separable C-star algebra is isomorphic to a subalgebra of BU. And you don't need a continuum hypothesis for this. Okay, so for this, we need just a few tricks. So first, I'll just say why is this true if I drop separable. So find B, actually, no, let's not call it B, maybe I should call it C. So this is step 1, such that A embeds into C for every separable A. So I'm not requiring C to be separable. Well, you can do all sorts of things. One easy thing is to just take C to be B of L2 of N. But by Gelf-Neimark, every separable C-star algebra is representable here. Okay, now what else can we do? Or just you could take just a product of all separable C-star algebras. Now you can say, well, they don't form a set. Well, you just look at a set of representatives and so on. So there are many ways to do this. You can also assure if we want C to be simple, for example, instead of B, you can take the Calkin algebra, which is simple, and again, every separable C-star algebra embeds into the Calkin algebra. Okay, and now what do we want? We want B. So take B to be elementary submodel of C. Like, so this is Levenheim's column theorem, and take B to be separable. Right, so I claim that this B works. Right, so fix A. Well, then what do we have? I want to prove that A embeds into the ultra power of B. Well, we don't know that yet, right? But we know that A embeds into C, right? And we also know that B is an elementary submodel of C. So what do we do next? So if you're a model theorist, you are wondering why am I not saying what I should be saying? Well, I'm not talking about universal theory or existential theory because we never talked about it. But of course, if you're a model theorist, you know a better, shorter proof of this using a little bit of theory. But I'm just asking you to forget about it for a moment. So use Levenhulme theorem to find separable D, which is elementary submodel of C, such that both, sorry, so that B is subset of D, and I need some name for this embedding. So let's call this C, and I want C of A to be also subset of D, and D is separable. I said it. Right. So if you give me any separable subset of any C-star algebra, I can find a separable elementary submodel which does this. So what do I have now? Well, look, because B is a subset of D, and both B and D are elementary submodels of C, we have that B is actually elementary submodel of D. Right, we mentioned this before, that this is one of the straightforward properties of the way that elementary submodel relation works. Right, so here is D. You just basically check that the type of any tuple here is the same as type of that tuple in C, but then it's same as the type in B. So B is elementary submodel of D. And now what this means, because D is separable, D embeds into the ultra power of U. This was the universality property of ultra powers that we used at some point. And since C embeds into A into D, but by composing maps, right, by composing A embeds into the ultra power of B. Right. So the right way to say this would be to talk about existential or universal theory of these algebras, but we don't need to do that. Well, we can move on to the next question. Suppose that A and B are elementarily equivalent, and that T is a type over the empty set. Prove that T is approximately satisfiable in A if and only if it is approximately satisfiable in B. Okay, so T, by the way, it was never claimed that T is countable, but countability makes no difference. So let's just fix some finite subset of T and epsilon greater than 0. Now T0 is finite. And now also it would be a good idea to say this is type in certain variables. Let's just call those variables X bar. It doesn't matter how many, there are only finitely many variables to care about. This is important, right? So there are only finitely many variables because there are only finitely many conditions here. So what is T0 of X bar? Well, it is now phi0 of X bar is equal to R0. Phi1 of X bar is equal to R1. Up to some phi, I don't know, k minus 1 of X bar is equal to Rk minus 1. Now we need to see what does it mean to be, what does it mean to approximately satisfy this? Well, let's just put all this in a single formula. So let's see. When I said formula, I should have said a sentence. Let's put all this in a single sentence. So let C be the following: infimum over all x bar. Now, okay, what do I mean by this? Well, x bar has certain sort. That sort is ranging over certain bounded ball. It doesn't matter what ball it is. But still, I'll just emphasize that we need to right. So this is quantifying over the sort of x bar of what? Now, some people like to take maximum, some people like to take sum. It makes no difference. I just take maximum. Maximum over j less than k of phi j of x bar minus rj absolute value. Right, so I'm just taking each one of these conditions, and what psi measures is whether T0 is approximately satisfied in whatever model we are evaluating this at. Now, remember, just keep in mind one thing, that inf is not equal to mean. This inf doesn't have to be attained unless you're in saturated model, but that's not the issue. So really, I'm pretty much ignoring this epsilon here, but it is important that we have some epsilon here. Okay, then okay, so psi to some, let's not talk about A or B, let's just talk about C. So psi as evaluated in C is equal to 0 if and only if for every epsilon greater than 0 there exists some C bar in C, again, of the appropriate sort. Right, so in all of our arguments, I just stayed at the unit ball, because these C algebras are so homogeneous, you can just quantify over the unit ball. There is no harm in that. But let's say of the appropriate sort, so that maximum over j less than k of phi j of C bar as evaluated in C minus Rj is less than epsilon. Okay, so now I'll just go and embellish my notation. I'll call this psi sub T0. Right, so from here, we have that T approximately satisfiable in C if and only if for every T0 finite subset of T, psi T0 in C is equal to 0. Right, this is exactly what this here says. Right, because this here is the definition, right? So for every finite subset, for every epsilon, you can get it arbitrarily close. But what is this? This is equivalent to saying, now question is, what is a theory? Is theory a functional, or is theory a set of sentences? But I'll just write it. Psi T0 is in the theory of C. If we think of theory as set of sentences, if you think of it as a functional, then it is in the kernel of theory. But anyway, so question was to prove that T is approximately satisfiable in A if and only if it is so in B, and basically if their theories are equal, then those two theories agree on each one of these sentences. So it is satisfiable in one if and only if it's satisfiable in the other. Okay, so I'm still keeping an eye on the chat. There are no questions, which I'll take as everything is clear. Now, next exercise uses conclusion of the previous exercise. And let's see, what does it say? So f, this is not f squared, sorry about this. So this is just footnote. Finite dimensional C-star algebra. Actually, you know, even this wasn't sufficiently general, even for separable. I mean, finite dimensional doesn't really matter here. For a separable C-star algebra, oh yeah, separable. Sorry, there was a reason why I said finite dimensional. You want nuclear. Okay, yeah. So I'll just erase separable and say later what is going on here. So prove that for a separable unital C-star algebra A, the following are equivalent. F unitally embeds into a relative commutant in the ultra power. Tensor product of countably many copies of F unitally embeds into the same algebra, and tensor product of Aleph-1 copies of F unitally embeds into this. Okay, so the only reason why I didn't say separable was that I didn't want to have to argue that this is unambiguous. You see, if C-star algebra is not nuclear, then potentially there is more than one way to define tensor product norm and tensor product. So I just wanted to avoid that. But other than that, if you assume that F is nuclear, or yeah, if you just assume that F is nuclear and separable, the same proof works. So how does this? Okay, so before we start proving any of the implications, well, actually, some implications are trivial. So clearly, 3 implies 2 implies 1, right? So all that we need to do is prove 1. And really, what we need to do is find the right model theoretic formulation of what 1 is saying. And this is the whole point, that the theory of A will see that this is going on. And the theory of A will see this for any separable C-star algebra. Okay, so assume 1. And now, so I'll just follow my hint. If you just wanted to do it for 2 by 2 matrices, you would just have to write down matrix units E11, E12, E21, E22, and just basically write a formula which tells you how they behave. But I really think that what I'm going to say is easier. So fix countable Q plus IQ subalgebra, or dense, countable dense subalgebra. Let's call it F0 of F. Right. So I'm just looking at this countable field, which is dense in the complex numbers, and just by hand choose a countable subalgebra F0 of F. And now just enumerate it. So it is AN for n in n. Okay, I may make this more complicated than necessary. Yeah, might be. Okay, so now I think it might have been a better idea if I just stuck to matrix units. But now that I'm here, okay, so I have to proceed. Now, Okay. Okay. So let T of xn for n in n Yeah, you know what? I'll just go with matrix units. Sorry, I may make it more complicated because yeah. Okay. So let's look at the following formula for n greater or equal than 1. Cn of x0 to xn minus 1 be the following. Infimum over all Okay, so I'll write down everything here. Y11. So okay, so I'm talking about matrix units right now. So infimum of y bar. I'll tell you what y bar is in a moment. Of the following. So we take maximum over j less than n of sorry, it's all in the indices. So I have to admit that I didn't think in advance. I guess it's obvious. I didn't think in advance about notations. So now it's taking the toll. So it's a maximum of, here you're taking norm of xj and yik plus maximum of, okay, actually I'll write separate formula. Let's call it phi of y bar. I'll tell you what phi is. So here, y bar is y11, y12, y21, y22. So it's a quadruple of variables of norm at most each one, at most one each one of them. So their sort is they belong to the unit ball, and what is phi of y bar says it is maximum of, well, I just need to write down what are the properties of matrix units. So over all I, j, and k, that norm of y, actually y, j, k, and l, yij times ykl, no, times yij k minus yik, comma, yij minus yji star, and what else? I think these are describing it. And also I want unital copy, so it's 1 minus y11 minus y22. I can add plus here. So this is phi. And unless I forgot something, I don't think. Yeah, So this describes the matrix units. And now what Psi says, or what it attempts to say, is that so for a fixed, actually let me write it down. Then Cn of some a0 through an minus 1 as evaluated at a is equal to 0 if and only if for every epsilon there is something in the algebra that looks arbitrarily close to the matrix units for M2 and that commutes arbitrarily well with these elements. Right. So for every epsilon, okay, I just said it, so I'm not going to write it here. And now, what is that equivalent to? Well, that is equivalent to so this was Psi, and now let theta n be supremum over all x0 to xn minus 1, Psi of x0 to xn minus 1. Now what Cn evaluated in A is equal to 0 if and only if for every n tuple in the unit ball of A, there is exactly the same thing as here, right? So there is arbitrarily well commuting, arbitrarily, there is something that looks like a copy of matrix units for M2, which commutes arbitrarily well with that n tuple. And now what is that equivalent to? Well, it is equivalent to the type, which, let me write it down. So let T of y11, y12, y21, y22 okay, so instead of writing the formulas, I'll just say that type asserts. Of course, type doesn't assert anything, but it is describing behavior of some formulas. So one, okay, shortcut that y bar commutes with all A in A. Now, A is separable. That's where we use this. You just can choose countable dense subset. You just want the countable type. So it commutes. And 2 y satisfies that formula that we call phi. Right. And so this is countable type. And this type, if it's satisfied, sorry, if it's satisfiable, then in the relative, then it's realizable in the ultra power. Okay, so T satisfiable in A is equivalent to M2 of C embeds into relative commutant of A in the ultra power, right? And before I go on, just you see here I described matrix units. Where was that? Right. So here I described matrix units, but what I started saying about countable dense Q plus IQ subalgebra, you can just write down in that type everything that you, I mean, all the relations between your elements. You know, basically you just need quantifier-free relations when product of two elements is the third one. I mean, something is called the quantifier-free diagram of the model, just description of the algebraic structure of it. And exactly the same thing would work. Okay, so finally, so all this work was here to prove a fact that M2 of C embeds into relative commutant if and only if theory has certain property, and that certain property is that this type is consistent. So we have proved that M2 of C embeds into this. Note, by the way, this doesn't depend on the ultrafilter. That's important. If and only if type T is satisfiable in A. Right? And this is the punchline. And actually, I could call this type T of M2 with understanding that if I replace M2 with some other separable algebra, I could just replace the appropriate type part of this type just by diagram describing what is going on. And now, by previous exercise, this here, okay, so this depends only on the theory of A. And this is the punchline, right? So satisfiability of some type depends only on the theory of A. And now we can proceed. So if M2 embeds into relative commutant, then by, let's call this star, M2 embeds into a relative commutant of B in its ultra power for any separable B such that B is elementally equivalent to A, right? Because A and B have the same theory, so the same types are consistent, and in particular, this one. Okay. And now we can proceed. So find A is equal to A0, elementary A1, elementary in A2, elementary, and so on. And they're all elementary submodels of the ultra power. And they're separable. And phi j, embedding M2 into AJ plus 1 intersected with AJ commutant for all J. Right, so how do we do that? Okay, we need one more page. How do we do that? Well, here is the ultra power. Here is A sitting at the bottom. we assumed that M2 embeds. So here is this embedding phi. A is A0, so this is phi 0 from M2 into here. Now take elementary submodel, right? Use Levitin's-Cohen theorem, find A1, but now A1 is elemental equivalent to A0. Okay, so the same types are satisfied, satisfiable over A1, but now A1 is elementary in the ultra power, which means that we can realize this type in bigger saturated structure. You see, you don't even need to prove that this ultra power of A to figure out what is its relation to A1. All that matters is that A1 is elementary submodel of AU, and AU is countably saturated. And so even without continuum hypothesis, all this is true, and therefore every type which is satisfiable in A1 is realized in AU, and realizing type gives you phi1 embedding into relative commutant, and then you just proceed, right? And just choose A2 again, same story, and you can just go on. Now, how far you can go? Well, if you go for countably many steps, you take union of what you have so far, and that is still separable submodel. And it's already elementary submodel. You don't even have to apply Levitin's-Cohen theorem, and just proceed. So you can go for Aleph 1 steps, right? So we have phi I mapping M2 into ultra power A. Now we can forget about AIs, which are unital. Oh, I forgot to say. So I is less than Aleph 1, right? Unital. And with commuting ranges. Right, so I made sure that the image of phi1 commutes with everything in A1. Well, I didn't really need everything in A1. I just needed the image under phi0 of M2. Right, so I get all of these are commuting. And now, because M2 is nuclear, or no, just no, it's 2 by 2 matrices, you have two unital copies of 2 by 2 matrices. What they generate is 4 by 4 matrices. Right, so the algebra generated by all of those is the tensor product. But I'll still say, since M2 is nuclear, as something of a warning sign here. So the C star algebra generated by the union of all those Fi of M2 is isomorphic to the tensor product of Aleph 1 copies of M2. Right, so this is not trivial for sure, but this is actually a theorem of Efros and Rosenberg. I mean, part of it. But just, you see, basically to prove it, you just need to put together different Lego blocks that we developed so far, right? So I mean, the messiest part was really in some sense, the easiest part, that you can write down this type, which describes that there is a copy of your algebra which commutes with given n elements. Now, it is important here, you see, that I had to do this. Actually, I glossed over this, I should say it. You see, why did I have theta n for every n tuple? Well, because why wasn't it enough just to say that for every element, there is a copy that commutes with it? Well, because we need to prove, once we talk about this type here, that it is consistent. So if fix a finite subset of the type, now that finite subset will mention finitely many elements of A. We don't know how many, but it's going to be some n, and then it's really the theta n that matters, right? So from there we get consistency of the type. Otherwise, argument just doesn't work. Yeah, and so that is this one. All right, next one. Oh yeah, right. So prove that every countably saturated C-star algebra of density character Aleph1 has cardinality Aleph1. And I did tell you this is a trick question. All that you need to prove is that the existence of such algebra implies CH. So really what you need to prove is that density character is continuous. Okay, so here is the step one, which is really the most interesting step and has nothing to do with model theory. So actually, I didn't call this. Okay. So if A is infinite dimensional, then A contains an abelian infinite dimensional C-star subalgebra. How do you prove this? I'll just sketch it. Choose, you see, by axiom of choice, by Zorn's lemma, if you want, you can choose the maximal abelian C-star subalgebra. Right, so just take union of chains. And now, if you assume that maximal subalgebra is finite dimensional, then you can prove that your algebra is really just algebra of matrices. Why is that so? Well, what does finite dimensional abelian algebra look like? It is just complex numbers to some nth power. Now, which means that in that algebra, you have these n orthogonal projections. And those projections have the property that this corner, PAP, is isomorphic to complex numbers. Why? Well, because you cannot add anything more to your algebra. And from there, you can basically find contradiction. There is a sketch of this in my book somewhere. So I'll just leave it at this. And this is what we really need. So all that we need is abelian infinite dimensional subalgebra. Now, what does that subalgebra look like? It is continuous functions on x. Okay, I never said unital, so I'll say C0 of x. And what is x? X is an infinite compact Hausdorff space. Okay, locally compact. So x is an infinite dimensional, locally compact Hausdorff. Okay, so what that means, here is our x. It means that you can choose countably many points, which so that each one of those points has an open neighborhood around. So basically, countable discrete set. Right, to just choose one. Yep. So choose xn in x, so that actually, so that for every n, there is open un neighborhood of xn, so that un intersected with un are empty for all n distinct from n. Okay, and now from there, by Tietze extension theorem or something, you can find in this algebra orthogonal positive elements. So find an for n in n such that 0 is less or equal than an less or equal than 1, norm of each an is 1, and an is 0 if m and n are distinct. Right, so that's simply because you are in this algebra C0 of x, and you can just use some peak functions around these x's, and those are the elements. Okay, and now we have such elements in our algebra. And now claim, okay, not claim, first, for some set S subset of n, define a type Ts of x as follows. So what are the conditions? First, okay, it's going to be generalized type. So let's say 0 is less or equal than x less or equal than 1. Norm of x is equal to 1. And then if I take xn, norm of xan minus an is equal to 0 if n is in S, and norm of xan is equal to 0 if n is not in S. Right, so what is x doing? It is picking exactly those ans whose indices belong to this set S, and it's orthogonal to the other ones. Right, so just think about you have A0, A1, A2, A3, and whatnot, and now you have elements. Let's say this is your set S, and what we are promising is that x goes somewhat like this. Okay, so now claim is that this type is satisfiable. Okay, it is satisfiable. I just made it unnecessarily complicated for me. Now I regret making this condition like this. Okay. Basically, what you need to do is, if you have a finite subset of the type, you just need to satisfy finitely many of these conditions, and almost some of. Okay, so let me. So so fix finite. No, that's T0 subset of Ts. Now, this finite type mentions only finitely many of the indices. So let n be such that T0 does not mention aj for j greater or equal than n. Right, and now what I would like to say is that I just take sum for aj for j less than n and j in S, that this should be partial realization, but that's not quite true. So what I need to do is vary about what is the end that I need to look at. So I'll take here, this happens sometimes, I'll take this aj to 1 over m. So for large enough n. Now, what is the point here? So if j is not in S, then Baj is 0, right? Because all of these are orthogonal to it. Now, if j is in S, then what is Baj? Well, it is Aj to 1 over m times Aj. And now this converges to Aj in the norm, right? Because these mth roots form an approximate unit for this algebra generated by Aj. So just for a large enough m, we can make this. So for any epsilon greater than 0, there exists an m so that norm of Baj minus Aj is less than epsilon for all j in S intersected with M. And that proves that each one of these types is consistent. All right. So back to algebra. So since C is countably saturated for every S subset of N, there exists some BS. Now let's call it CS. There's some CS such that CS AJ is AJ if J is in S, and CS AJ is 0 if J is not in S. But now, if S is different from S prime, then CS minus CS prime, we want to estimate this. So how do we estimate this? Actually, maybe I shouldn't be saying this. Okay, then fix J, which is in S but not in S prime. I just swap the sets if necessary, like so it belongs to one and not the other, right? So then not AS, CS. CS AJ is equal to AJ, and CS prime AJ is equal to 0, right? So CS minus CS prime times AJ, the norm of this is at least 1. Actually, it is 1. And this here is less weak with the normal CS minus CS prime. Right. So what we have is a discrete set of cardinality continuum. Therefore, CS for S subset of N is discrete, right? And this is a metric space, and therefore the density character of C is at least continuum, right? And therefore continuum is equal to all F1, right? Because assumption was the density character was all F1, and from there, what was the? I forgot what was the question. Correct. So we have this algebra of density character all F1 continuum hypothesis holds. Now, what is the cardinality of S? C. Okay, so how do we estimate cardinality? Well, fix a dense subset. Now, every element, because this is a metric space, for every element, there is a Cauchy sequence inside the dense subset converging to your element. So this is at most density character of C to the power of Aleph 0, right? And now what is this? This is Aleph 1 to Aleph 0. Okay, so okay, so let's do it. So Aleph 1 is less or equal than 2 to Aleph 0. So it's 2 to Aleph 0 to Aleph 0, which is 2 to Aleph 0, which is Aleph 1. Right, so basically, I just did this computation here at Aleph 1 to Aleph 0. This is equal to continuum because of this. Okay, so the main trick here was finding this type. Let's see. Okay. Right. So the next question is about was about ultra powers of Banach spaces. Yeah, I didn't think this was going to take the entire class. I thought I'll just do this in 20 minutes. So okay. Right. So question was to prove that every ultra power of the Hilbert space is fully saturated. Now, you know, to a model theorist, just there is a one-line proof. This is theory of Hilbert spaces is omega is kappa categorical for every uncountable cardinal kappa. Therefore, it's omega stable, end of the story. All uncountable models are saturated. But of course, I didn't assume that you would know that. The point number one is that this categorical thing, if you have two Hilbert spaces, if they have the same dimension, they're isomorphic. So write it in this way. So if H prime are, okay, I'll say infinite dimensional Hilbert spaces, and I'm not going to say dimension, I'll talk about density character. So, and density character of one is equal to density character of the other. This is actually dimension. It is an exercise to check that for infinite dimensional space, if you have a dense subset of cardinality kappa, then orthonormal basis has cardinality at most kappa, and vice versa. Right, then they are isomorphic, isometric. Okay. Now, second is that ultra power of Hilbert space is a Hilbert space. This can be proved in more than one way. Probably the easiest way is just to look at H. Okay, you have norm, fine, but just throw in the inner product. I mean, this is what model theorists would call expansion of the structure. So just take ultra power of this, right? And then just check that inner product still behaves like inner product. This is just Walsh's theorem. Right, so this is Hilbert space. And then you may forget about inner product and just say, well, the norm comes from inner product. Or if you feel more like an analyst, there is a theorem of von Neumann that characterizes those Banach spaces that are Hilbert spaces by parallelogram inequality. Equality, and you can just use that and say, well, okay, so this by Walsh it holds, but no, you can just do it this way. So anyway, so ultra power of Hilbert space is a Hilbert space, and now what do we need to do is 3, and this was the tricky part, and this is a general thing. So if a type T of X is satisfiable in A, so A here is anything, cyst algebra, Hilbert space, whatever, then it is realized in some ultra power of A. Proof of this is your typical Zorn's lemma construction. So you have type which is satisfiable. Now, of course, if type is countable, we know that. But problem is that type is maybe not countable. Well, okay, so you have uncountable type. And now you just need to define appropriate index set, which is going to be a set of all conditions in your type, but also set of all positive rationals. And then no, actually it's your subsets. Okay, so anyway, you need to devise appropriate set and find filter. Basically, you have a net of these finite subsets of your type and their realizations. You just need to find a big ultra filter so that for every finite subset, there is something that realizes that finite subset which belongs to the ultra filter. So there is some work here. And from here, it should be clear. So just once again, we are proving that every ultra power is fully saturated. So fix U, and now we have L2N U is isomorphic to some L2 of some index set I. Okay, now fix T type over L2 of I. And now what is important is that cardinality of the type is more than cardinality of I, right? So fully saturated means every type of smaller cardinality is satisfied. Right? When I say cardinality of type, I mean number of conditions in the type less than I. Well, then there is some subset of I, so that conditions in I mention only those basic elements whose indices come from there. So here is I, and here is some IT, which is a smaller subset. Now, we know that this type is satisfied in some bigger Hilbert space. Okay, right, so this is what I should have said before. In case of Hilbert spaces, if type is satisfiable in our algebra, then it's realized in some ultra power, but that ultra power is a bigger Hilbert space. So this is going to be Hilbert space again. Oh yes, actually I should have added one more thing before I proceeded. Let me just move this down a little bit. Okay, this was not good. Okay. So this is 4. If I is subset of J, then L2 of I is an elementary submodel of L2 of J. This really follows from what we said before, because you know what you can just play with ultra powers and Levenheim's column theorem and check that this is indeed true. You see, because you know L2 of I is an elementary submodel of its big ultra power. Now, if you take elementary submodel of that, it is going to be of this form. And Levenheim's column gives you the one of the appropriate size. And now this is it, right? So this So this type, this L2 of IT is elementary in L2 of IT ultra power, but it's also elementary in L2 of I. And this one is elementary here, but realization of type depends only on countably many of those basic vectors. And since I minus IT is definitely infinite, you can just find an automorphism, isometry of this Hilbert space, which moves all of those basic vectors into here, and you have realization in here. So I'm basically saying more than necessary. I think just really everything follows from these previous parts. I think there was one more. Oh yes, right. So this one. So you have cyst algebras, natural embedding of ultra power of tensor of ultra powers into ultra power of the tensor in surjective, if and only if at least one of them is finite dimensional. The converse implication is easy. It's really the forward implication. And we actually use a trick from one of the previous questions that so because both A and B are infinite dimensional. Okay, so actually I have to say how I'm proving this. Suppose A, B are infinite dimensional, and now find AN for n in N in A such that 0 is less or equal than AN less or equal than 1, norm of AN is equal to 1, and AN is 0 if M is distinct from N, right? That trick using a maximal abelian subalgebra. And the same thing for B. Oh, these are in A. And 0 less or equal than Bn. Norm of Bn is 1. And Bn is 0 if M is distinct from N in B. Right, so we have these orthogonal, infinitely many orthogonal elements of the positive norm. Now, in A tensor B ultra power, there exists some C positive contraction, which has the property that C times AM tensor BM is equal to AM tensor BM for all M, but C times AM tensor Bn is equal to 0 if M is distinct from N. This is literally the same lemma that we used in the previous question. So this is just, so in place of those ANs, you have AM, BM. This is a positive element, by the way. Right, so it's tensor product of two positive elements. It's a positive element. So we're really looking at, I think I called it S. So S is subset of N squared. All right, so S is simply the diagonal set of all pairs MM from M in N. And by applying that lemma from before, we get element like this. Now, however, in the tensor product of the ultra powers, AU tensor BU, there is nothing like that because this is, okay, maybe I should start the sentence differently, but is the completion of things of the form sum I less than n of some xi tensor yi for n in n, xi in A and yi in B, and nothing in this completion can approximate an element C like this, right? So sketch of the proof, just fix small enough epsilon, something like 1/4 is more than enough. If you if C exists, you can approximate it by finite sum of elementary tensors up to 1/4. Well, just check it; it's not going to work. That there is some problem with this diagonal here. Okay, so this was the sketch. Let me know if you have any questions. As I said, I still have to look at the solutions. So I guess if you thought about these questions, it probably what I was saying makes more sense. If anything doesn't make sense, let me know. I'll be happy to elaborate on that. And I'll also be happy to go back to the regular course next Friday. And on Friday also, I'll post the next problem set. All right. Okay, so it was good to see you, and take care, and thank you, and talk to you soon, I hope. Okay, bye.